In this module of Chapter 8 on Human Demography, Module 8.5, I will cover several aspects of human demography, including lifespan evolution, examples of human mortality trajectory and a life table, and human age-specific migration patterns. My postdoc, Deborah Judge, and myself, in Judge and Carey 2000 publication, estimated the evolved lifespan of both early hominids and modern humans by regressing the average body size corrected for brain volume on lifespan in anthropoid primate subfamilies. Note the graph here with million years ago on the x-axis and predicted lifespan for various species on the y-axis. We noted a major increase in longevity from the 52 to 56 years of Homo habilis to the 60 to 63 years for Homo erectus, between roughly 1.7 and 2 million years ago. Our analysis indicated that the evolved lifespan of modern humans is between 72 and 91 years. We noted that it was probably extremely rare for early hominids to live this long. This lifespan resulted in a primate, that is Homo sapiens, with the potential to survive long beyond a mother's ability to birth young. This literature suggests that the postmenopausal survival is not an artifact of modern lifestyle, but may have originated between 1 and 2 million years ago, coincident with the radiation of hominids out of Africa. This formulation is important because it takes cessation of reproduction, that is menopause, as a hominoid given, and it suggests that kin selection was a critical component to prolonged longevity in humans. Human mortality. An example of age-specific mortality curve, QX, for humans is presented in this figure using U.S. female mortality in 2006. This is a classic J-shaped mortality curve with several interesting features. First, infant, that is first-year mortality, is high. It then drops to a life course low at around 10 to 11 years. At this point, the one-year death rate is around 1 in 8,000. Second, there is a teen mortality bump, primarily due to an increase in risky behavior. It's most prominent in males. Finally, after age 30 and continuing until the late 80s or early 90s, there is an exponential increase in mortality at a yearly Gompertzian rate of 8%. Human life table. An example abridged life table for modern humans in a developed country is presented in this table for U.S. females in 2006. Note the first column is age X in 5-year increments, followed by columns containing NX, LX, PX, QX, DX, and EX. Several aspects of this table merit comment. First, a remarkable 96% of newborn females survive to age 50. That is to say, less than 4% of newborns have died in the first 50 years. By their early 80s, only half of this newborn cohort are dead, as shown in the LX column, a point that is also reflected in the 80.2-year expectation of life at birth. Less than 1 in 1,600 5-year-old girls die in their next 5 years. Over 25% of 80-year-olds die in the next 5 years, and over 90% of centenarians die in the next 5 years. The life table shows that nearly 1 in 5 of all deaths in a newborn cohort occur between 80 and 85. Finally, less than 2% of the newborns survive to 100, at which time these centenarians have, on average, only 2 more years to live. Migration patterns. Migration in humans is age-specific. Young adults in their early 20s show the highest migration rates, and young teenagers the lowest. This is because the migration rates of children mirror those of their parents, and therefore the migration rates of infants exceed those of adolescents. The general age pattern of migration is the sum of 4 mathematical components, including a single negative exponential curve of the pre-labor force ages, a left-skewed unimodal curve at the labor force ages from mid-teens to late 60s, an almost bell-shaped curve at the post-labor force ages, that is late 60s to late 70s, and a constant term to improve the overall fit. This ends this module on human lifespan, human mortality, life table, and migration.